Okay, I want to talk to you now about how to calculate work when you're pumping a liquid out of a conical tank. This is just another one of those examples for how to calculate work. So with that, let me erase this off. And we'll start with an example. What I'm talking about is you have a conical tank, comes down a certain height. And we'll just say that this one is 5 meters. And we'll say the radius up here is 3 meters. Okay, what else do we need to know? We need to know probably where the height of the liquid is. So why don't we just say that's 1 meter from the top of the tank. Okay, which would make it 4 meters from the bottom. You also need to know where the spout is. So we'll say the spout is coming off the top of the tank. Water is leaving the very top of the tank. So you need to calculate the work to pump all of the water out. Okay, oops, there we go. All right, so looking at this, it's all in the setup at first. So I'm going to take my tank and I'm going to tip it on its side. So I have something that looks like this. Okay, and my tank is going to sit here like that. This is the y-axis. This is the x-axis. And so in this notation, gravity is going to be pulling down this way. Okay, we know the y value here because that's just the radius of the tank at the top of the tank, and that's 3 meters. We know that this is 0 because it comes down to a point, but we know that distance is going to be 5 meters. So what we care about right here is just this line to define the shape of the tank. So that's going to be our f of x. And if you look at it, it's just a straight line to go from the intersect with the y-axis down to the x-axis. So that means I just have the y-intercept is 3, and then my slope is just, let's see, change in y or change in x. The slope is going this way, negative 3 over 5x. Okay? So that's the original shape function. And then we'll work to area next. So what is area? So we want area as a function of x. Well, the area we're talking about is this cross-section area right there. So if you look at it, wherever we are along the x-axis, due to this function, we know the height of that cylinder right there. So if we know the height, that's that radius right there. So area equals pi. We're rotating around this whole shape around the x-axis. So it's creating a circle. So the area of a circle is pi r squared. Area as a function of x equals pi f of x squared. The f of x, again, r equals f of x. There. So if I carry this out a little bit more, area x equals pi, and my f of x is negative 3 over 5 x plus 3 squared, quantity squared. Okay, and if I need to continue, because it's going to be a lot easier if I can separate it out, so I'm going to multiply that out to pi equals, let's see, 9 over 25x squared minus, and it works out to be 18 over 5x plus 9, and that's my area as a function of x. Boom. For that shape rotated around the x-axis. Okay, so the next step, we're going to take this, I'll move over here, and I'm going to say volume equals integral from b to a. So what is b to a? That would be the height of the liquid right here. So as we said here, and we rotated everything to its side, so if I move everything to its side over here, the liquids would start at 1 and end at 5. So here's my B, and here's my A. So I have this. No, I'll keep it generic for now. So I'll do area as a function of x, dx. So what is dx? Dx is, if I take a section here, it is, remember in previous sections we called this delta x. Well, in this notation, that delta x is put in as dx here, representing that there is a height to it. But when we do an integral, that gets absorbed into the integration. Okay, so this is what we got. What does it mean now? So as I said, B and A, so 5 to 1, okay, and then my area is pi 9 divided by 25, x squared minus 18, 5x plus 9 dx. Okay, so that's just the volume portion of calculating the work. Now, of course, we have to have that volume times the density, which density is 1,000 kilograms per meters cubed for water, and gravity is 9.8 meters per second squared. Okay, so work equals force times distance. Work equals, so the integral, it's going to look just like this here, 5 to 1. So we're putting in the volume component. I'm going to leave off the dx. I'm going to put that right over, way over here, because I still need to squeeze in my distance right here. Okay? But the rest of this so far is, oops, I forgot something. I forgot my density, which is 1,000 times 9.8. I'm going to erase that, correct my mistake. Move this a little bit further. dx. So I put in the density of water times gravity, and this gives me all of that force component that I need. I just need to insert distance. So distance is going to be, I made it simple by turning things on its side. It means as we move along, because the spout is right up here at the top of the tank, x, whatever value of x, is the distance that I have to plug in here. So I've seen it tested other ways where if you have it around the y-axis, you might have to do the top of the tank minus the value of y where you're at. I'll add that to the next video. So, but I do want to move along on this one. So this is looking pretty straightforward now. I just have to take this x and multiply it in to the rest of the x's in this parentheses. So I'm going to have work equals, Actually, let me put all my constant stuff out in front. So this value right here is 9800. Okay, I have a pi still out here. And then I got my integration, 5 to 1. And now I'm going to distribute this in here. So this now becomes 925x cubed minus 18 divided by 5x squared plus x, or 9x dx. Okay, so we're almost done. I'm just going to squeeze in at the bottom, do a quick integration on that, and then I'll leave it at that. So 9800 pi. So quick integration, this is 9, I have to put a parenthesis here, I hate to do that, over 100 x to the fourth minus 15 under 18 to the third plus 9 divided by 2x squared, and that is from 5 to 1. Okay, so hopefully you can work that out, and as you can see the 1 down, sticking down there. Work that out, and that'll equal your work. Okay, so hope this helps. It's all in the setup. I'm going to add another example on this pumping liquids, but more in a manner that I saw it on a test from another university. So that you can kind of see how setup is really important and how your answers can come out. But hopefully this helps you get a basic understanding of what's going on. Subscribe to my channel so you can see the updates. I'll try to stay ahead of your syllabus. But anyway, good luck.